Hi students, welcome to the 6th lecture in permutations and combinations. In this lecture we are going to give hints for exercise 5a problems. So before going into the hints, let me recall what are the topics that we have discussed in the first 5 lectures. So in the first 5 lectures we have discussed about fundamental principle of counting, both multiplication and addition. So multiplication in the sense, so if a task can be divided into two works W1 and W2, then the number of ways of completing the task. Number of ways of completing this task is equal to number of ways of doing W1 times number of ways of doing W2. And coming to addition, if a task can be performed in two formats, W1 and W2, then the number of ways of completing the task is equal to number of ways of completing W1 plus number of ways of completing W2. So here what you have to remember is whenever end comes, you have to do multiplication. Whenever R comes, you have to perform addition. So these are the basic things that you have to remember throughout this chapter. And then we have defined factorials. So I think by this time you are familiar with factorials, so I'm not recalling factorials. And then we have defined linear and circular permutations. In a linear permutation, we arrange things in a row, whereas in a circular permutation, we arrange things in a circle. So the differences between linear permutations and circular permutations are, in a linear permutation, we have the notion of first position, second position, and so on up to last position. Whereas in a circular permutation, we don't have first position, second position, and so on. So in a circular permutation, we can define the position of a object with respect to another one. So here I can say that B is to the right of A, and C is to the right of B, and D is to the left of A. But here, whereas in a linear permutation, just I can say that A is in the first position, D is in the last position, C is in the third position, and so on. So in a linear permutation, I can specify the place without referring to the other objects. Whereas in a circular permutation, I cannot specify the place without referring to the other objects. In a circular permutation, we need reference. In a linear permutation, we don't need any reference. And a few linear permutations result in a single circular permutation. And then we have this theorem. Number of permutations of n distinct objects taken are at a time. In general, it is denoted by NPR. NPR is equal to n times n minus 1 times n minus 2, so on up to n minus r plus 1. Or else we have this formula n factorial upon n minus r factorial. So here we should not read it as NPR, we have to read it as number of permutations of n distinct objects taken are at a time. And then we have few problems related to this one. So NPR is equal to n times n minus 1 p r minus 1. So we have given two different proofs for this one. One is based on the formula and the other is based on combinatorial arguments. And then we have another result. NPR is equal to n minus 1 p r plus r times n minus 1 p r minus 1. So this term r times n minus 1 p r minus 1 stands for number of permutations of n distinct objects taken r at a time, which always contain a particular element. NPR stands for number of permutations of n distinct objects taken r at a time. N minus 1 p r stands for number of permutations of n distinct objects taken r at a time without containing a particular element. Therefore, the total number of permutations is equal to number of permutations without containing a particular element plus number of permutations which always contain a particular element. These are the results that we have proved. And then while solving few problems, we have derived these formulas. The number of the sum of all r-digit numbers that can be formed using the n digits is equal to n minus 1 p r minus 1 times sum of the given digits times 1111 r times. And then if 0 is included in these n digits, then we have this formula. N minus 1 p r minus 1 times sum of the given digits times 1111 r times minus n minus 2 p r minus 2 times sum of the given digits times 11111 r minus 1 terms. So why we are discarding this term means, so all the r digit numbers that begin with 0 is same as saying we are having r minus 1 digited numbers. R digited numbers starting with 0 is same as r minus 1 digited numbers. So we have counted these r minus 1 digited numbers also. So we have to exclude these r minus 1 digit numbers. So if you exclude these r minus 1 digit numbers, then this is the actual sum. So if 0 is not there, we have to use this formula. If 0 is there, we have to use this formula. And then we have derived the number of a formula to find out the number of injections from a set A with m elements to a set B with n elements. The number of injections is going to be npm, or number of 1-1 functions is going to be npm, as long as m is less than or equal to n. When m is greater than n, we will not have any injection. And then we have this formula for derangements. So whenever you have a problem related to derangement, you have to use this formula. And the formula goes like this: n factorial times 1 by 2 factorial minus 1 upon 3 factorial plus 1 upon 4 factorial and so on up to minus 1 whole to the power of n times 1 upon n factorial. And these are the few results that we have proved. Anyway, we haven't given the proof for derangements. It is not there in the textbook. But once we complete principle of inclusion and exclusion, we can give the formula, we can give the proof for this derangement also. So before solving the problems in 5A, there is one problem which is related to specific order. And this specific order is not discussed in example problems. So before going into exercise problems, first let me discuss what you mean by this specific order. Okay, so let me take this example. So suppose you are in an exhibition and you have to shoot these 5 smileys. The number of ways in which you can shoot these 5 smileys is going to be 5 factorial. So you can shoot any of these 5 smileys first, and after that you can shoot any of the remaining 4. After that you can shoot any of the remaining 3. So the total number of ways in which you can shoot these 5 smileys is going to be 5 factorial. Suppose on the next table you have this kind of arrangement. So here you have 7 smileys, 1, 2, 3, 4, 5, 6, 7. So now these 3 smileys are attached like this. So these 2 smileys are on the top of this one. So here I cannot shoot this smiley first. If I shoot this smiley first, then these 2 smileys are going to fly away. If I shoot this middle smiley, then this top smiley will fly away. So there is a specific order in which I have to shoot these 3 balloons, or we have to shoot these 3 smileys. So first I can shoot this smiley. After shooting this smiley, I can shoot any of the remaining 4 here, and then I can come back to this one. So after shooting this one, I can again go back to any of the remaining 4, and then I can shoot this one. Or else first I can shoot this one, and then I can shoot this last one, and then I can shoot this one, and then I can shoot this second one, and then I can shoot this 6th one, and then I can shoot this one, and then this one. So there is a specific order in which we have to shoot these 3 smileys. So I can shoot this second smiley only after shooting this first one, and I can shoot this third smiley only after shooting these 2. So after shooting this smiley, I can take a break, and then I can come back to this one. I can take a break in the sense I can go back and I can shoot these smileys, and then I can come back this one. So the total number of ways in which I can shoot these 7 smileys is not going to be 7 factorial. Here the answer is going to be 5 factorial. The number of ways in which I can shoot these 5 smileys is going to be 5 factorial. Here the number of ways in which I can shoot these 7 smileys is not going to be 7 factorial, because there is a specific order on these 3 smileys. So if you want to answer this question, so first let me take few simple examples and then we can see. Now look at this question. The number of ways in which I can arrange these three objects A, B, C is going to be 3 factorial. Now look at this second question. In how many of these arrangements A and B will come together? So A and B will come together means whenever you have a problem like this, you can tie up A and B, and then we can treat A and B as a single unit. Now you have 2 units. You can arrange these 2 units in 2 factorial ways, and in this 1 unit I can arrange A and B in 2 factorial ways. Therefore the total number of ways in which A and B come together is equal to 2 factorial times 2 factorial. Now look at this question. In how many of these arrangements B comes after A? So this question is different from this one. So in the previous question, A and B should come together. So in this question, B should come after E. B should come after A means, okay, so let me give you an example. CAB or CBA. So in these two arrangements, A and B are coming together. In these two arrangements, A and B are coming together. But in this arrangement, B comes after A. But here B is not coming after A. So when I ask you to count in how many arrangements A and B come together, these two will come. I have to count these two examples for the second option. For the second question. Whereas if I want to answer the third question, I am supposed to count only this one. Because in this arrangement, B comes before A. Okay. Now let us try to answer the third one. In how many arrangements B comes after A? So these are the 6 arrangements that we have. So out of these 6 arrangements, we are not interested in this one. Why we are not interested in this one means in this arrangement, B is coming before A. And similarly in these two arrangements also, B is coming before A. So I am interested in only these 3 arrangements. Therefore the total number of arrangements in which B comes after A is going to be 3. So answer for this question is 3. So since we have only 3 objects, I can list down all the permutations and then I can search for the required permutations. Okay. Now what happens if you have 4 objects? The total number of ways in which I can arrange these objects A, B, C, D is going to be 4 factorial. In how many of these arrangements A, B, C come together? A, B, C come together means I have to tie A, B, C. After tying A, B, C, I have 2 units. Now I can arrange these 2 units in 2 factorial ways. And in this 1 unit, I can arrange this A, B, C in 3 factorial ways. Therefore, the total number of arrangements in which A, B, C come together is equal to 2 factorial times 3 factorial. Now look at this third question. In how many of these B comes after A and C comes after B? So in how many of these arrangements B comes after A and C comes after B? So there is a difference between the second question and third question. So if you want, I can give an example. D, C, A, B. So this is an arrangement in which all the 3, A, B, C are coming together. This is an arrangement in which A, B, C are coming together. But in this arrangement, B comes after A, okay, but C is not coming after B. So I can count this arrangement for the second question, but I cannot count this arrangement for the third question. So definitely the number of arrangements in which A, B, C come together is going to be more than the number of arrangements in which B comes after A and C comes after B. Now these are the 24 permutations that we have there. That means these are the 4 factorial permutations that we have using A, B, C, D. Now look at this permutation A, B, C, D. So in this permutation B is coming after A and C is coming after B. Sorry. But out of these 6 permutations, I can take only this one. Why I can take only this one means in the remaining 5 permutations, these remaining 5 permutations violate this condition. Therefore, out of these 6 permutations, I am interested in only 1 permutation. Similarly, here we have these 6 permutations. Out of these 6 permutations, I am interested in only this one. Here also, out of these 6 permutations, I am interested in only this one. In these 6 permutations, I am interested in only this one. Now, if I fix this D, I can arrange this ABC in 3 factorial ways. I can arrange this ABC in 3 factorial ways. But out of these 3 factorial arrangements, I am interested in only 1 arrangement. So these 3 factorial arrangements give rise to a single permutation. The total number of permutations that I have is 4 factorial. So every 3 factorial arrangements give rise to a single permutation. So how many total permutations are there which satisfy the third condition is the question. So you can answer this question like this. I have 4 factorial rupees and I want to buy pens, and each pen costs 3 factorial. The cost of each pen is 3 factorial and I have 4 factorial rupees. Now how many pens I can buy? The number of pens that I can buy is 4 factorial upon 3 factorial. So here also the total number of permutations is 4 factorial, and every 3 factorial arrangements give rise to a single arrangement which satisfy this condition, third condition. Therefore the total number of arrangements in which B comes after A and C comes after B is going to be 4 factorial upon 3 factorial. So this is our answer. And then we can generalize this one. So the generalization is like this. So we have n distinct objects. In these n distinct objects we have a specific order on k objects. The number of permutations is going to be n factorial upon k factorial. Because those k factorial permutations result in a single permutation and the total number of permutations is n factorial, therefore the number of permutations which satisfy that specific order is going to be n factorial upon k factorial. Now you can answer this question. Now you have these 7 smileys and the specific order is imposed on these 3 smileys. Therefore the total number of ways in which you can shoot these 7 smileys is going to be 7 factorial upon 3 factorial. This is your answer. I hope the specific order is clear for you. Now you can solve all the exercise problems on your own. But anyway, let me give the hints for few exercise problems. So you have to write down the notes for all the exercise problems. So this is our first problem. First problem in the sense, this is the 6th problem in the textbook. The first 5 problems are based on the expansions of NPR. So I leave those 5 problems for you. The statement of this problem is like this. A man has 4 sons and there are 5 schools in his reach. In how many ways he can admit his sons in these schools so that no 2 sons go to the same school? So first try to understand the question. Here we have 4 sons and 5 schools. Now the question is, we have to admit these people in these schools so that no two sons go to the same school, or no 2 children go to the same school. Now the first son has 5 options, second one has 4 options, third one has 3 options, fourth one has 2 options. Therefore the number of ways in which these 4 sons can be admitted in these 5 schools is going to be 5p4. Number of ways is equal to 5p4. Why the answer is 5p4 means, we have already seen this question. There are 4 people and 5 chairs. In how many ways you can arrange these 4 people in 5 chairs? Since we cannot make 2 people to sit in the same chair, we have to arrange these people in 4 different chairs. So here also we have 4 sons and 5 schools, and the condition is we have to admit these 4 sons in different schools. So this problem is same as this problem. We have 4 people and 5 chairs. Number of ways of arranging these 4 people in 5 chairs is 5p4. Number of ways of arranging these 4 people in 5 chairs is 5p4. So if you understand this one, then you can answer this one. Okay, so let us move on to the next question. The next question is like this. If there are 25 railway stations on a railway line, now how many second class single tickets should be printed so as to make a passenger to commute between these stations? So let me explain the question for you. There is a railway line, and here you have the first station, second station, third station, and so on up to 25 stations. Now a person wants to move from one station to another station. Suppose you want to move from station number 3 to station number 12. So what you have to do is you have to go and buy a ticket at station number 3 to station number 12. So on the ticket we have, this is the ticket we have. So on the ticket we will have from station and to station. So there are 25 different stations. And now we have these two blanks. The first blank is from and the second blank is to. In how many ways we can arrange these 25 stations in these two places? Number of ways of filling these n objects in r places. Number of ways of filling n objects in r places is equal to npr. So the answer is going to be 25p2. So this is the ticket we have from address and to address. From address in the sense from station and to station. So if you buy a ticket from 3rd station to 12th station, you can travel only from 3rd to 12th. I cannot travel from 12 to 3 back. Okay, so here also from station and to station. So after filling the first blank with any of the 25 stations, in order to fill the second blank, we have only 24 options. I cannot buy a ticket from station number 2 to station number 2. So I can buy a ticket only from station number 2 to station number 6 or one station to other station. So these two blanks must be different. Different in the sense I cannot fill the same object in these two blanks. So we have n objects and we have r blanks. Number of ways of filling these n objects in r blanks is equal to npr. So here n is equal to 25 and r is equal to 2. Okay, coming to the next problem. There are 30 students in a classroom. On a New Year day, each student wants to greet the other students with a greeting card. Now how many greeting cards are required? So this is the question. There are 30 students. Now here also we have a greeting card. On this greeting card we have from and to. So from means you can write your name, to means you can write the other name. Other name in the sense you can write the remaining 29 names. So here also we have these two blanks. The first blank is from and the second blank is to. You cannot post a greeting card written by you to yourself. So the first blank can be filled in 30 ways. The second blank can be filled in 29 ways. So both the problems are same. Both the problems boils down to NPR, number of ways of filling n objects in r places. So here also the answer is going to be 30p2. 30p2 in the sense 30 times 29. So these many greeting cards are required. Now look at this problem. Find the number of ways of arranging the letters of the word triangle so that the relative positions of vowels and consonants are not disturbed. We had done similar kind of problem in examples. Anyway, let me repeat the question for you. So we have this, let me do the triangle. Now what are the vowels here? T is a consonant, R is a consonant, I is a vowel, A, N, G, L, E. So we have this triangle. So how many letters are there? 8. If there are no constraints, then the number of ways of arranging these 8 letters is equal to 8 factorial. But here we have a constraint. The constraint is vowel should be occupied by vowels positions and consonant should be occupied by consonant positions. So I can arrange this I, A and E among these 3 places only. And the remaining places I can arrange these consonants. So consonants has 1, 2, 3, 4, 5 blanks. We have 5 places for consonants, and these 5 places we can fill with these things. Therefore, the total number of ways of arranging these things is equal to 5 factorial times 3 factorial. Or else you can divide this task into two parts. W1 is to arrange vowels. W2 is to arrange consonants. Number of ways of doing W1 is equal to 3 factorial because there are only 3 vowels. And number of ways of doing W2 is equal to 5 factorial. Therefore, the total number of ways of doing the task is equal to 3 factorial times 5 factorial. Coming to the next problem, find the sum of all 4-digit numbers that can be formed using the digits 0, 2, 4, 7, 8 without repetition. So you have to find the sum of all 4-digit numbers formed using these digits. But unfortunately, in one of the digit is going to be 0. So we have two formulas. One formula is when 0 is not included in the given digits. One formula is when 0 is included in the given digits. So here 0 is included in the given digit. So we have to use the second formula. And the second formula is like this. Sum is equal to n minus 1 p r minus 1 times sum of the given digits times 1 1 1 1 r times minus n minus 2 p r minus 2 times sum 1 1 1 1 r minus 1 times. So if you use this formula, then you can solve this one. So here n is equal to 5 and r is equal to 4, and sum is equal to 0 plus 2 plus 4 plus 7 plus 8. So it is a direct application of the formula. So whenever you have formulas, you can directly use the formula. If you don't remember the formula, then you have to follow the actual procedure. Okay. Find the number of numbers which are greater than 4,000 that are formed using the digits 0, 2, 4, 6 and 8. So we have to find how many numbers are there which are greater than 4,000 formed by the digits 0, 2, 4, 6 and 8. So there are 5 digits 0, 2, 4, 6 and 8. These are 5 digits. Okay. Now we have to find how many numbers are there which are greater than 4,000. So greater than 4,000 means we'll have all 5-digit numbers. All 5-digit numbers are greater than 4,000 plus all 4-digit numbers starting with 4 or 6 or 8. So if you can find out the answers for these two things separately, then you can add. So how many 5-digit numbers I can form using the digits 0, 2, 4, 6 and 8. So 5-digit numbers means I have these 5 digits 1, 2, 3, 4, 5 places. So here 0 is there. So I cannot fill the first blank with 0. So I can fill the first blank in 4 ways. So after filling the first blank in 4 ways, we have 4 more blanks and we have 4 more objects. So I can fill those 4 more objects in these 4 blanks in 4 factorial ways. So the total number of 5-digit numbers is going to be 4 times 4 factorial. Now how many 4-digit numbers are there which starts with 4, which starts with 6 and which starts with 8? So I have to form 4-digit numbers 1, 2, 3, 4. I can fill the first blank with either 4 or 6 or 8. So in order to fill the first blank, I have 3 options. So once I fill the first blank with one of these things, I will be left with these 3 blanks. and I will be left with only 4 objects. So the number of ways of filling these 4 objects in these 3 blanks is equal to 4p3. And the number of ways of filling the first blank is 3. Therefore, the total number of ways of filling these 4 blanks is equal to 3 times 4p3. So these are the total number of 4-digit numbers which are greater than 4000. And these are the total number of 5-digit numbers which are greater than 4000. Therefore, the total number of numbers which are greater than 4000 means this plus this. So you have to write down the statements separately. I am just giving the hints. You have to solve the problem. Solve the problem is you have to write down the statement. Number of 5-digit words that can, number of 5-digit numbers that can be formed using the digits 0, 2, 4, 6, 8 is equal to this one. And number of 4-digit numbers starting with 4, starting with 6, and starting with 8 is equal to this one. So you have to write down these statements separately. Then only you can understand permutations and combinations. Now, coming to the next problem. Find the number of ways of arranging 5 mathematics books, 4 physics books, and 3 chemistry books in a row such that the books of the same subject come together. So let us write down the information that we have. There are 5 mathematics books, 4 physics books, and 3 chemistry books. On the whole, how many books we have? 5 plus 4 plus 3, which is equal to 12 books we have. If there are no constraints, I can arrange these 12 books in 12 factorial ways. But the constraint is we have to arrange in such a way that all mathematics books and all physics books and all chemistry books should come together. So whenever you see coming together, what you have to do is you have to tie up all mathematics books, all physics books, and all chemistry books. So after tying up all mathematics, physics, and chemistry books, we have 3 units. I can arrange these 3 units in 3 factorial ways. And in this unit of 5 mathematics books, I can arrange them in 5 factorial ways. And in this one unit consisting of physics books, I can arrange them in 4 factorial ways. And in this one unit of chemistry books, I can arrange them in 3 factorial ways. Therefore, the total number of ways of arranging these books so that all the books of the same subject come together is equal to 3 factorial times 5 factorial times 4 factorial times 3 factorial. Why we have this 3 factorial means we have these 3 units. Why we have this 5 factorial is we have 5 mathematics books. Why we have 4 factorial means we have these 4 physics books. And why we have these 3 factorial means we have these 3 chemistry books. Therefore, the total number of ways of arranging the books such that all the books of the same subject come together is equal to 3 factorial times 5 factorial times 4 factorial times 3 factorial. Next, we have this problem related to specific order. Anyway, we have discussed that specific order, so we can directly write down the answers here. Okay. So, in a class containing 10 students, A1, A2, A3, so on up to A2, A10. In how many ways we can arrange these students such that A1, A2, A3 sit together? That is our first problem. The second one is A1, A2, A3 sit in a specific order, and third one is A1, A2, A3 sit together in a specific order. So first of all, you have to understand the difference between these 3. So I think the first one is clear for you. A1, A2, A3 sit together. Okay. Now the second one is A1, A2, A3 sit in a specific order. So in this lecture we have discussed about specific order. So I think the second statement is also clear for you. Now the third statement. A1, A2, A3 sit together in a specific order. A1, A2, A3 sit together means first of all we have to tie up A1, A2, A3. So after tying up A1, A2, A3, I am not supposed to arrange this A1, A2, A3 in whatever manner I want. I can arrange A1, A2, A3 in a specified order in only one way. Okay, let us answer these questions separately. The first one, A1, A2, A3 come together. So whenever you see A1, A2, A3 coming together, we have to tie up these A1, A2, A3. So after tying up A1, A2, A3, how many objects we have? We have 7 plus 1, 8 objects. I can arrange these 8 objects in 8 factorial ways. Now, in this one unit consisting of A1, A2, A3, I can arrange them in 3 factorial ways. Therefore, the total number of ways of arranging these 10 students is equal to 8 factorial times 3 factorial. These are the total number of arrangements in which A1, A2, A3 come together. Now, the second one. Specific A1, A2, A3 come in a specific order. Sit in a specific order. So let us fix the specific orders. The specific order that we can fix is A2 is sitting first, after that A1, after that A3. So what do I mean by A2, A1, A3 means A1 should sit only after A2 and A3 should sit only after A1. So this is the specific order that we have. The total number of objects is 10 and we have a specific order on these 3 objects. Therefore, so we have this formula n factorial upon k factorial. If there are n objects, the number of permutations is going to be n factorial. But if there are k objects on which we impose specific order, and the total number of arrangements is going to be n factorial upon k factorial. So here the specific order is imposed on these 3 objects. Therefore, the answer is for this one is going to be 10 factorial upon 3 factorial. Now the third one. A1, A2, A3 sit together in a specific order. So whenever you see A1, A2, A3 sitting together, we can just tie up A1, A2, A3. So after tying up A1, A2, A3, we have 8 units. I can arrange these 8 units in 8 factorial ways. But after arranging these 8 units, okay, in this unit consisting of A1, A2, A3, I am not supposed to arrange A1, A2, A3 in whatever manner I want. So I have to follow only this specific order. So in this one unit consisting of A1, A2, A3, I can arrange A1, A2, A3 in only one specific order. If the specific order is like this A2, A1, A3, then I can arrange this A1, A2, A3 in only this order A2, A1 and then A3. So I will not have this extra 3 factorial here. So the total number of ways of arranging is just 8 factorial. So this is our answer. Answer for the third one. So first of all, you have to understand the difference between these 3 statements. If you understand the difference between these 3 statements, then the answers are going to be easy. A1, A2, A3 sitting together, A1, A2, A3 sit in a specified order, and the third one is A1, A2, A3 sit together in a specific order. So A1, A2, A3 sit together in a specific order means we have to tie up A1, A2, A3, but unlike in the first option, we are not supposed to permute A1, A2, A3 in whatever manner we want. We have to arrange A1, A2, A3 in a specific order. Okay, coming to the next, we have few problems related to rank. Okay, so let us look at this problem. If the letters of the word master are permuted in all possible ways and the words thus obtained are arranged in dictionary order, then find the rank of the words REMAST and MASTER, master. Okay, so for this what you have to do is you have to write the given letters in dictionary order. So the given letters are master, MASTER. So you have to write these letters in dictionary order. So the letters in dictionary order is going to be A, E, M, R, S, T. So these are the 6 letters that we have. Now we can have 6 factorial permutations, which is equal to 720. So we have 720 permutations using these 6 letters. Now what we have to do is we have to arrange these 720 permutations in dictionary order. After arranging all these 720 permutations in dictionary order, what we have to do is we have to search for these words. The position where this word REMAST is located is called the rank of the word REMAST. and the position where master stands is called the rank of the word master. So first let us solve the first one. So finding the rank of REMAST. So in dictionary we have these pages. The first page begins with A, and the second page begins with E, and the third page begins with M, and the fourth page begins with R, and the fifth page begins with S, and the sixth page begins with T. These are the only alphabets that we have in the dictionary. So we can have words using these things. Okay. Now I have to look for this word REMAST. So this REMAST will not be in first page, second page, third page, will be in the page starting with R. So before coming into this page, I have to count how many words are there in the first 3 pages. So our required word will be in this page, which begins with R. Therefore, we have to count number of words which begin with A, number of words which begin with A, which is going to be 5 factorial, because we have these 6 letters, 1 2 3 4 5 6. So I have to arrange this first blank with A. After arranging the first blank with A, we will be left with 5 blanks, and we will be left with 5 letters, and I can arrange these 5 letters in these 5 blanks in 5 factorial ways. Therefore the total number of words that begin with A is 5 factorial, plus number of words that begin with E. Number of words that begin with E is also again 5 factorial, plus number of words that begin with M, which is also 5 factorial, plus I cannot count all the words that begin with R, because if I count all the words that begin with R, our REMAST will be among one of those words. So here I have to be a little bit careful. So I cannot count all the words that begin with R. So now what we do is, after entering into this page, the first few words will begin with RA, and the next few words will begin with RE, and the next few words that begin with RM, and the next words begin with RS, and the next words begin with RT. So in this page we have few words that begin with RA, and we have few words that begin with RE, and we have few words that begin with RM, and we have few words that begin with RS, and the few words that begin with RT. Now our required word REMAST. So our required word begins with RE. So I cannot search for this one in RA. So I have to add all the words that begin with plus all the words that begin with RA. Number of words that begin with RA is going to be 4 factorial. Because we are filling the first 2 blanks with R and A, so we'll be left with 4 more blanks. So those 4 blanks can be filled with 4 remaining letters in 4 factorial ways. Okay, plus the next thing is, so in order to not get confused, we have already used the word R, or we have already used the letter R. We have this dictionary order A, E, M, R, S, T. So we have already used this letter R. Now I cannot count all the words that begin with RE, because our required word REMAST begins with RE. So what we do is, we have to further divide this division. So after RE, the next letter is going to be A. So I have to count all those words that begin with REA. So all the words that begin with REA is going to be 3 factorial. And the next thing is all the words that begin with REM. But our required word REMAST begins with REM. So I cannot count all the words that begin with M. So what I have to do is I have to further make a division. So I have used M also, REMA. I have to count all the words that begin with REMA. But our required word begins with REMA. So I cannot count all the words that begin with REMA. So I have to make the further division. I have to see how many words are there which begins with REMA and the next letter is S. I cannot count all the words that begin with REMAST because here we have REMAST. So the next letter is going to be T. So how many words are there which begins with REMAST? There is only one word. Therefore the total is, therefore rank of REMAST is, we have how many 5 factorials here? We have 3 5 factorials. 5 factorial plus 5 factorial plus 5 factorial plus here we have 4 factorial plus 3 factorial plus 1. So this is the rank of the word REMAST. So no need to expand all these things. You can leave the answer as it is. Just by looking at this answer, we can understand whether you have mastered the rank problems or not. Okay. Next, we have to calculate the rank of the word MASTER. So we have to calculate the rank of this word MASTER, and the letters in alphabetical order are A, E, M, R, S, T. So our master starts with M. So I have to count all the words that begin with A and I have to count all the words that begin with E. So number of words that begin with A. Number of words that begin with A is going to be 5 factorial plus number of words that begin with E is again 5 factorial. Now I cannot count all the words that begin with M. So here I have to be a little bit careful. I am making a further division here, plus I have to count all the words that begin with MA. But unfortunately our master M starts with MA. So here also I have to be a little bit careful. I have to make a further division. I have to count all the words that begin with MAE. So number of words that begin with MAE is going to be 3 factorial. Because I have filled the first 3 blanks with MAE, so the remaining 3 blanks can be filled in 3 factorial ways. Now after MAE I have to count all the words that begin with, I have used MAR. I have to count all the words that begin with MAR, which is again going to be 3 factorial. Plus I have to count all the words that begin with MAS. But here unfortunately master starts with MAS. So here I have to be a little bit careful. I have to make a further division. So here I have used I have used MAS. So after that the next alphabetical order is E. I have to count all the words that begin with MASE, which is going to be 2 factorial. And next I have to count all the words that begin with MAE, After E, MASR. MASR again 2 factorial plus all the words that begin with MA after R MAST. But unfortunately master starts with MAST. So here I have to be a little bit careful with this one. So I have used MAST. After that the next letter is E. All the words that begin with MASTE. But master starts with MASTE. So here also I have to be a little bit careful, and here I have to make the further division MASTER. Number of words that begin with MASTER is 1. Therefore the total rank of the word master is, we have to add all these things. Therefore rank is equal to 5 factorial plus 5 factorial plus 3 factorial plus 3 factorial plus 2 factorial plus 2 factorial plus 1. So you can leave the answer as it is. So these are the 2 rank problems that we have in this exercise. Let us look at the next problem. If the letters of the word bring are permuted in all possible ways and the words thus obtained are arranged in dictionary order, then find the 59th word. So it is also considered as a rank problem, but in the previous problem what we have done is we have arranged all the words in dictionary order and we are going to find the rank of the given words. But here we have to arrange all the permutations in dictionary order. After arranging all the words in dictionary order, now we have to look for the 59th word. Okay, so first let us write down the given letters. So the given letters are BRING. The first thing that you have to do is you have to write the letters in dictionary order. So the dictionary order here is going to be B, G, I, N, R. Okay. Now the first page begins with B, the second page begins with G, and the third page begins with I, and the fourth page begins with N, and the fifth page begins with R. So we have these 5 pages here. Now we have to look for 59th word. Now let us see how many pages, how many words are there in each page. Since we have 5 letter words, so how many words start with B? Number of words that begin with B is going to be 4 factorial, which is 24. Similarly, number of words that begin with G is going to be 4 factorial, which is 24. And similarly, number of words that begin with I is going to be 4 factorial, which is 24. 24 plus 24 is 48. 48 plus 24 is 72. But we want 59th word. Therefore, our 59th word will not be in the first page, will not be in the second page, it will be in the third page. So, the 59th word begins with I. So if I add this 4 factorial, then the number exceeds, the number goes beyond 59. So I should not count all the words that begin with I. Therefore, the first letter in the required word is going to be I. The first letter in the required word is I. Now we have to find the remaining 4 letters. The first letter in the required word is going to be I. Now we have to find the remaining 4 letters. Okay. B-R-I-N-G. So B, G, I, N, R, B, G. Let me check whether I have written it correctly. Okay. Now I should not count all the words that begin with I. Number of words that I have used I. This is my first letter. Now after I, the next letter is B. Number of words that begin with IB. With IB, the number of words is going to be 3 factorial, which is equal to 6. So 48 plus 6, which is equal to 54. Okay. Now we can add number of words that begin with so after IB we have IG. Number of words that begin with IG is also 3 factorial which is equal to 6. So if I add 6 to 54, it is going to be 60. So our required word will begin with BG. Our required word will begin with, our required word begins with IG. So the first letter is I and the second letter is going to be G. So this is my first letter and this is my second letter. So I should not count all the letters that begin with B, mean IG. I should not count here. So what we have to do is we have to further divide this one. Further divide this one means number of words that begin with after I, G, I can add B. So the number of words that begin with IGB is going to be 2 factorial, which is 2. So if I add 2 to 54, it will be equal to 56. So 56 is still within our reach. So we are not exceeding 59. So I can count all the words that begin with IGB. So there is no problem. Next, number of words that begin with after IGB, I can have IGN. With IGN, still I will have 2 factorial words, which is 2. So if I add this 2, then I will have 58. So 58 is still in our reach. I am not exceeding 59. Next, number of words that begin with so IG, after IGN we have IGR. So here we have 2 factorial words, so which is 2. So if I add this 2 to 58, then it's going to be 60. So here we are crossing 59. Therefore here we have to be careful. I cannot take all the words that begin with IGR. So I should not count all the words that begin with IGR. So here I have to make the further division. That means the third letter in the required word is going to be R. The first letter is I, the second letter is G, and the third letter is R. Now we have to search for the fourth letter. That means number of words that begin with IGR. After IGR we can start with B because that is our next alphabet. So with IGRB we will have one word, one factorial words which is equal to 1. So I can add this 58 plus 1 which is 59. So this one word is going to be our required word. So the required word is going to be, the fourth letter is B, and therefore the fifth letter is going to be N. Therefore the required word is going to be our 59th word. The first letter is I, and the second letter is G, and the third letter is R, and the fourth letter is B, and the fifth letter is N. So this is our 50. Coming to the last problem, there are 9 objects and 9 boxes. 5 objects cannot fit in 3 small boxes. How many arrangements can be made such that all the objects can be placed in boxes each? So this is our problem. So what is the information that we have? We have 9 objects and 9 boxes, out of which 5 objects cannot fit in 3 small boxes. So they have given that 5 objects cannot fit in 3 small boxes. That means we have 3 small boxes and 5 big objects. We have 5 big objects, 1, 2, 3, 4, 5, and the remaining 4 are relatively small, 1, 2, 3, 4. And now we have 3 small boxes, 1, 2, 3, and the remaining boxes are little bit big, 1, 2, 3, 4, 5, and 6. There are 9 boxes, 3 are small and 6 are relatively big. And there are 9 objects, 5 are relatively big and 4 are small. These 5 objects cannot fit in these 3 small boxes. Now, how many arrangements are possible such that each object is placed in one of the boxes? Now here what we have to do is, I cannot fit these 5 objects in these 3 boxes. So what we have to do is, first we have to fill these 5 objects in these 6 boxes. So what is our W1? W1 is to fill 5 big objects in 6 boxes. So this we can do it in 6p5 ways. So why we have 6p5? We can treat these 5 as 5 people, and we can treat these 6 boxes as 6 chairs. We can, in the number of ways in which 5 people can sit in 6 chairs is going to be 6p5. Okay. Now W2 is to fill the remaining boxes with remaining objects. So how many objects are left out? 4. And how many boxes will be left out? 1 big box and 3 small boxes. So we have these 4 objects that are left out, and we have one box and 1 big box and 3 small boxes are left out. So this we can do it in 4 factorial ways. Therefore the number of ways of doing W2 is equal to 4 factorial. The total number of ways of completing the task is equal to number of ways of doing W1 times number of ways of doing W2, which is equal to 6p5 times 4 factorial. So this is our answer.